Hello everyone. In this lecture, we will try to understand the operation of inverting and non-inverting op-amps in the simplest possible way. In fact, if you understand this part of op-amp lecture, you will be able to understand other lectures relatively easily. We will derive expressions for output voltage or voltage gain of the operational amplifiers. The figure shows an op-amp circuit with input voltage Vin, output voltage V0, feedback resistor RF, and input resistor R1. The other input of the op-amp is grounded. The relatively new word here is feedback that you see in the feedback resistor RF. Let us try to understand the word feedback in very simple words. Feedback is the information at the output which is given to the input for effective running of the system is called feedback. Let me give a simple example. Assume that you are driving a car on a highway. Obviously, you will be driving at a speed of 100 kilometers per hour. Now, if you are about to enter a zigzag road, what you will do? You will reduce the speed such that you will not meet with an accident. Here, the output is speed. This information is processed in your brain and you take appropriate action by reducing accelerator, thereby reducing the speed when you enter a zigzag road. That is a simple example of a feedback system. Let us look at the feedback system of op-amp. There are two inputs in case of op-amp: inverting and non-inverting. For linear operations, output is fed back to the inverting input terminal. Linear operation is when output varies linearly with input signal, then we get linear operation. For generating oscillations at the output, that is for generating waveforms, etc., output is fed back to non-inverting terminal. Output is fed back to non-inverting terminal for generating waveforms or oscillation. For non-linear applications like comparator, there is no feedback. And the output is always either positive VSAT or negative VSAT. This is a simple explanation about feedback in op-amp circuit. You also can give your feedback on my lectures at ebpaul.lectures@gmail.com. One important thing I wanted to mention here is, in the next few lectures, we will discuss about linear op-amp circuits where feedback is given to inverting terminal. Well, we will look at inverting and non-inverting op-amps. If the input is given to inverting terminal, then it is called inverting op-amp. If the input is given to non-inverting terminal, then it is called as non-inverting op-amp. In few moments, we will see the reason for them being called so. The virtual ground is one of the most important concepts we must understand to solve the problems in op-amps with negative feedback. Op-amps will have very high voltage gain. Let the open loop gain of operational amplifier, represented as AOL, is equal to 10 to the power of 6. Assume that the op-amp is working in linear region, then the output voltage is always less than VSAT. Let us assume that VSAT is equal to 10 volts. Substituting in the output voltage expression, V0 is equals to open loop gain times difference voltage at the input. From this expression, the difference voltage V plus minus V minus is equals to 10 to the power of minus 5. This is very small value which can be approximated to 0. Therefore, non-inverting voltage V plus minus inverting voltage V minus is equal to 0, or V plus is equal to V minus. V plus is equal to V minus. That is, the voltage at the inverting terminal is equal to the voltage at the non-inverting terminal when the op-amp is working in the linear region with negative feedback. Voltage at the inverting terminal is equal to voltage at the non-inverting terminal. Here non-inverting terminal is at ground potential. Therefore, the inverting voltage also is at ground potential. Let me repeat one more time. The voltage at the inverting terminal is equal to voltage at non-inverting terminal when the op-amp is working in the linear region with negative feedback. Another important assumption we make is the input currents entering into op-amp are 0. That is, I plus is equal to 0 and I minus is equal to 0. Both I plus and I minus are 0. The reason for that is, at the input of operational amplifier, there is a differential pair of MOSFETs. At the input of each MOSFET, there is a MOS capacitor, and the current flowing through this capacitor is ideally 0. Therefore, input current of op-amp is 0 and the input impedance is infinity. These are the two important assumptions we make while solving the problems. The first one is inverting and non-inverting voltages at the input of op-amp are same, and the second one is the currents into op-amp are 0. These assumptions make the analysis of op-amps relatively easy. V plus is equal to V minus and I plus equal to I minus is equal to 0. Now let us derive the expression for the voltage gain of inverting op-amp. Voltage gain is defined as the ratio of output voltage to the input voltage. Here signal is given to the inverting terminal. From figure 1 we can see that V plus terminal is grounded. From the first assumption we can say that the node voltage V minus is also at ground potential because both of them are equal from first assumption. V plus is 0, therefore the node voltage V minus is also equal to 0. Also, the currents entering into op-amp I plus and I minus, both of them are 0. This is like open circuit at the input of op-amp. Let me remove the op-amp as there is no current flowing into the op-amp. This results in a circuit which looks like this. Applying both conditions results in a simple circuit shown in figure 3. This is basically op-amp circuit after incorporating the assumptions. The op-amp circuit with assumptions applied is more or less like a series circuit shown in the figure 3. Let I1 be the current flowing in the resistor R1. IF is the current flowing in the feedback resistor RF. Because it is a series circuit, the currents flowing in the resistors are same. Therefore, I1 is equal to IF. The current I1 is the ratio of voltage drop across the resistor R1 to the resistor R1. Similarly, the current IF is the voltage drop across resistor RF divided by RF. Also, From virtual ground concept, substituting V minus equal to 0 in equation 3, we get the expression for the output voltage, which looks like this. Solving this expression, the voltage gain AV, which is the ratio of output voltage to the input voltage, it is given by minus RF by R1. The negative sign indicates that there is a phase shift of 180 degrees between input and output. Another important aspect is the gain of the op-amp can be varied by varying external resistors RF and R1 and without really worrying about the internal structure of op-amp. This is the best part of operational amplifiers. The gain of the amplifier can be controlled externally by changing the external resistor values alone. If the input is a sine wave, the output will be an inverted sine wave in case of inverting operational amplifier. And the gain is 5. You can see from the scale over here. So in this particular input and output waveforms, you can observe that there is a phase shift of 180 degrees. There is a phase shift of 180 degrees. Now let us derive the expression for the voltage gain of inverting operational amplifier with 2 inputs. The op-amp has 2 inputs V1 and V2. You can have n number of inputs. Following the same procedure as we have done previously, you can derive the expression for output voltage. Applying KCL at node N, this is I1 plus I2 is equal to IF. Using Ohm's law, I1 is V1 minus V minus divided by R1. I2 is V2 minus V minus divided by R2, which is equal to V minus minus V0 divided by RF. From virtual ground concept, V minus is equal to 0. Therefore, substituting V minus is equal to 0 in this expression, you will get the expression for output voltage is equal to minus RF by R1 into V1 minus RF by R2 into V2. If R1 is equal to R2 is equal to RF, if all the resistor values are made same, then the output voltage is equals to minus V1 plus V2. Inverting operational amplifier with many inputs works like an inverting summer. That is, the output voltage is the sum of input voltages with minus sign. This can be achieved by appropriately choosing the values of resistors. If R1 is equal to R2 is equals to RF, then output voltage is equal to minus of sum of input voltages. However, there is a sign which is negative. If you were to get rid of this negative sign as well, then connect an inverting operational amplifier with a voltage gain of 1 here. So in that case, the output voltage will be straightforward sum V1 plus V2 without any phase shift. Now we will move on to non-inverting op-amp. Here the input signal is given to non-inverting terminal of the op-amp. One important aspect you must remember in non-inverting op-amps is regarding the resistors R and RG. Practically no current flows into op-amp. Therefore, a provision must be made for currents to flow into ground. Resistor R provides a path for currents to the ground in the feedback path, and the resistor RG provides a path for currents to the ground from the input voltage Vin. Therefore, these two resistors will provide a path for the currents to flow into ground as no current enters into op-amp. Now let us take a simple non-inverting configuration where there are no resistors at the input of non-inverting terminal. From the concept of virtual ground, V minus is equals to V plus, which is equal to V in, and we also know that I plus is equal to I minus is equal to 0 as no current flows into op-amp, that is input currents are 0. By applying these two conditions for op-amp shown in figure 1, it will result in a simple series circuit shown in figure 2. In a series circuit, the currents are same, therefore I is equal to IF. Applying Ohm's law, we will get the expression as shown here. 0 minus V minus divided by R is equal to V minus V naught by RF. Substituting V minus, which is equal to V in the above equation, we will get V in by R is equal to V in minus V naught by RF, which is equal to V naught is equal to 1 plus RF by R into Vn. Therefore, the output voltage of non-inverting amplifier without any input resistors is equal to the output voltage V naught is equal to 1 plus RF divided by R into Vn, the input voltage just before the op-amp. And the expression for voltage gain, which is nothing but the ratio of output voltage to input voltage, is equal to 1 plus RF by R. And there is no phase shift between input and output voltages. The phase shift in case of non-inverting operational amplifiers is 0. Now let us extend the analysis with the input resistors R1 and Rg. If you observe the output voltage, previously V in was here. So if I call this as V in dash, then V naught is equals to 1 plus RF by R into V in dash. Now we need to relate V in dash with V in. Basically it is a voltage divider circuit. From the voltage divider circuit R1 and Rg, and if you give a notation of V plus for this, then V plus is nothing but Rg by Rg plus R1 into V in, a voltage divider circuit. Clubbing both these expressions, then the final expression for the output voltage of a non-inverting operational amplifier is 1 plus RF by R into Rg by Rg plus R1 into V in. This expression and this expression together, put together, you will get this expression. As said earlier, there is no phase shift between input and output voltages. Now we will move on to non-inverting op-amp with two inputs. This is also called as non-inverting summer. The inputs are V1 and V2. Like we have done previously, the same way let us first relate output voltage with a non-inverting voltage V plus. Output voltage V naught is equals to 1 plus RF by R into V plus. The next step is we need to relate V plus with V1 and V2. Now let us apply KCL at node N. Let me call the current flowing through the resistor R1 is I1, current flowing through the resistor R2 is I2, and the current flowing through the resistor Rg is Ig. Applying KCL at node N, I1 plus I2 is equal to IG. I1 is V1 minus V plus divided by R1. I2 is V2 minus V plus divided by R2. And Ig is V plus minus ground potential, which is 0, divided by Rg. Substituting in this expression I1 plus I2 is, and solving by equaling all the resistors, then we will get V plus is equal to 1/3 of V1 plus V2. Also, let us make another assumption. Rf is equal to 2R. Therefore, from the equations 5 and 6, the output voltage V0 will become equal to V1 plus V2. As said earlier, there is no phase shift between input and output voltages. Now let us solve a problem, inverting operational amplifier problem. So let's find the voltage gain of the inverting op-amp. So in this particular circuit, RF is given 5 kilo ohms and R1 is given as 1 kilo ohms. The voltage gain is given as AV is equals to V0 by Vin, which is equal to minus RF by R1. Therefore, the gain of this particular operational amplifier is minus 5. Inverting sign represents a phase shift of 180 degrees between input and output waveforms. Let us solve a simple problem on non-inverting op-amp. So in this particular problem, we are going to find out the voltage gain of non-inverting op-amp. We know that the voltage gain of non-inverting op-amp is given by AV is equals to V0 by Vin, which is equal to 1 plus RF by R. Therefore, substituting, we will get the voltage gain of non-inverting amplifier is equal to 6. You can observe that there is no phase shift between input and output voltages. In summary, the important thing that you need to remember is using two assumptions for solving op-amp problems. The first one, virtual ground concept, where the inverting and non-inverting voltages are same when you are operating the op-amp in linear region. And the second important assumption is the currents entering into the operational amplifier is equal to 0. Substituting these two assumptions makes this operational amplifier circuit a very simple series R circuit as shown in this particular figure. So appropriate usage of these two assumptions will help solve the op-amp problems relatively easily. Thank you.